Hello, everybody. Welcome back to another session of 10 minutes of learning. So, we'll start with a very important concept today, which is known as the power factor. Power factor is something that is very important and is generally denoted by cos theta. Please note that power factor is applicable only for AC power and not for DC power, not for DC power. Because as you must all of you must know that power, when it's DC, then we consider it as V into I only, that is voltage into current. But when power becomes AC, then there are a lot of complications that arise. Out of that, the real power in AC is given by VI cos theta, and there is something which is also VI cos theta is also known as active power. And there is another power which is known as the VI sine theta, which is known as the reactive power. And finally, we have the apparent power, which is nothing but the vector summation of this active and reactive power. So I'll come to them step by step. Please remember these three powers are for AC only. Okay. Now, where lies the difference? This is one of the fundamental questions that students ask me all the time. So for DC power, see, it's very simple. Voltage is a static value. Voltage has a static value. Current can change with the load, and then approximately because of the voltage and current, the power changes, which is as per the norms of the DC power. So let us just forget this for a while and go to the next slide for a detailed description of what the vector summation between this active power and reactive power means for bringing to the apparent power, and how is power factor that plays a very important role for making up the active power or the useful power in a AC power system. So see, all of you know Pythagoras theorem, right? Please pardon my drawing skills, they're not that much good. Suppose this is a right angle triangle. The base is taken as the resistance, perpendicular is taken as the reactance, and Z, that is impedance, is taken as the hypotenuse. This angle is theta. So we all know that sine theta, for in this case, will be the perpendicular by hypotenuse. Cos theta will be equal to base by hypotenuse, right? In this case, if perpendicular hypotenuse, that means x by z, that is your sine theta, and this is r by z, right? Now from the sorry, now from this triangle we can see that z is equal to obviously r square plus x square. Am I right? So if you replace the value of this z here and here, then these two expressions become x by root over of r square plus x square, and this becomes r divided by root over of r square plus, correct? So now I want to bring to your attention a very interesting thing which is called the phasor diagram. So you must have known and learned vectors. Suppose this is the vector representing the voltage V for a AC powered circuit. Now, if you have only a resistor in the circuit, then we know that the current through a resistor is in phase with the voltage. That means the current, whatever it may be its magnitude, it will fall on the same straight line as the voltage, and the current due to the resistor will end somewhere here. And this is governed by V is equal to I R. That is Ohm's law. Very easy, right? Also, now if this AC powered circuit has got some inductance, suppose that inductance is given by L. You also know this that L cannot be considered. The unit of L is in Henry. So we cannot consider L directly in a circuit. So what we need to do, we need to consider something called as reactance. X, if it's inductive reactance, then it is given by omega L, where omega is equal to pi F into L, where F is the frequency of the circuit. That means whatever the sinusoid that's running for the voltage and the current, whatever the frequency is, that frequency is given here as F. Okay, so if the current for XL is always at 90-degree lagging to the voltage, you know this, all of us know this. Now if we make a vector summation between these two, we'll see that the final current comes to somewhat here. This is final current IZ, which is obviously IR square plus IL square, and this angle will be theta, or the power factor angle. Okay, got the point? Now see, if L increases, what happens? L increases, XL increases. If XL increases, this is obviously again governed by I into XL. If I is constant, if V is constant, I has to go down. And then finally what happens? This angle that we are talking about, that angle changes its value. That means these X changes its value. As a result, power factor changes its value. And as a result, what happens? This power, which is the active power, that also changes its value. So P, through an active AC power, if VI cos theta given by VI cos theta, if cos theta increases, that means goes towards 1, then this also increases. But if cos theta decreases, this also decreases. Okay, so cos theta is an important parameter in calculating the true power or the active power of a AC circuit that we have established. Now, how it impacts the actual scenario, let me explain that in the next slide. So we started with two values of power. One is VI cos theta, another is VI sin theta. So now if you see that if cos theta increases, sin theta will decrease. But if cos theta decreases, sin theta will increase, right? Okay, that's how it happens because the cos square, we know this from trigonometry. This has to be kept constant, right? If this increases, this will decrease, and if this increases, this will decrease. Okay, now let us just take a small example to show how it implicates your real life. Suppose you have a heater, power of which is 2000 watts for a heater, and you also have a AC, the power of which is the same, 2000 watts. I've got an air condition. So by experience, we know that cos theta for this heater is approximately zero point 0.9, whereas for this AC, cos theta is approximately zero point 0.8. So let's see how this pans out in the real life scenario. For both the cases, we'll consider the supply voltage to 200 volts of RMS. Clear? So for the heater, next slide. Let's go to the next slide and see. So for the heater, we have got 2000 as the power requirement of the heater. We have got supply voltage 200, which you cannot change. Current into the power factor. How much was it? 0.9. 9. Means I will be equal to 2000 divided by 200 into zero point 0.9. That makes it 10 by zero point 0.9, which is equal to 11.11 amperes. Clear? Now for the AC, let us make the same calculation. The AC for running, it also needs 2000 watts. It is also supplied with 200 volts, but the AC has a power factor of 0.8. In this case, I becomes 2000 by 200 into zero point 0.8, which gives 12.5 amperes. So, can you see the very basic difference how power factor affects the supply current? Please note that this current is the single most important thing based on which the electric bill comes at your house. Okay, so for a heater consuming that same 2000 watt load, and for this AC consuming the same 2000 watt load, you have a better power factor, zero point 0.9 for the heater, but a traditionally worse power factor for the AC, that is zero point 0.8. So with a better power factor, the heater consumes a lesser current, and lesser current means lesser electric bill. And the AC consumes 12.5 amperes. That means it is a little bit on the higher side, which consumes a more electric bill, right? So from here, we can derive one thing, that is the apparent power. The last slide on today's video, the apparent power for AC circuits is given by V into I, that is 200 into 11.11 in case of a heater, and 200 into 12.5 in case of a AC. Now this is measured in VA, volt amperes. It's not given in kilowatts or watts, guys, because this is the apparent power that the electric utility has to supply to your home for making the heater or the AC work. Understood? So this apparent power is given by VA, and it's for a better power factor. It is between it is lesser for the heater, and for a worse power factor, it is more for an AC. So finally, we can say that the power factor cos theta, which is from 0 to 1, if you have an appliance, the power factor of which is closer to 1, then you are saving electricity more. If you have a appliance which is closer to 0, then you are going to pay through your nose. Okay, so see you again. Today's session, a simple session on power factor, ends here. Hope you have enjoyed it, and please leave your comments and feedback below. Thank you.